So this was another attempt at me not trying to have a talk at Netdev that failed miserably, but Jamal, I did, I failed twice, so yeah, shame on me on the first one. So anyway, this is something that Jamal kind of floated out onto the list recently for us to say, like, hey, you know, a lot of us in this room know each other pretty well. We've known each other for a long time. We all have our own quirks about how we do our work. Like I've got a little trick that I do on how I debug kernels, or I might have a little trick on how I trace packets through the network stack. And it might be something that you might do really well, and someone else might not do it very well at all. And we thought, wouldn't it be nice to see if people want to come up and share what they do, right? A lot of these presentations over the years have always been like, here's this setup, and here's like how we ran it, and here's our lovely numbers. And one of the questions inevitably is, how did you run the test, right? So this BOF was really kind of thought of as, let's try to share that, see who wants to talk about it, share their foo. And I think we have a few people online that are going to try to present remotely. So we'll see how it goes. Like, may go great, may end really fast, but I encourage you to ask questions of everyone talking. The pizza will stay hot, so don't fret. So I guess we'll get rolling.
Hi. Okay. Don't breathe. Okay, so this is I want to share something with everyone. It's really impromptu, but I feel compelled to share it. So this is about a tool called RedSnoop, and this is written by my friend and colleague Andrei Nakriko, who also works at Meta. So RedSnoop is basically a tool that's built on top of the BPF probe infrastructure, and it essentially allows you to kind of at runtime, at dynamic runtime, trace any function that you can kprobe. You can also trace it with RedSnoop, and what it will give you is it will give you a very lovely stack trace. It will also tell you what each function returned. And by default, you can only use it, well, by default, it will only report failure cases, so anything that returns like a negative number. But you can also tell it to give you, all cases, including successful ones. And another useful feature, I'm not sure if it's it's mentioned here. But there is also a LBR mode, which is, oh, here we go. That's one example. Yeah. So there's also like an LBR mode where it will also tell you, it will also attempt to give you like a more detailed stack trace. And I found this incredibly useful when working on the kernel and debugging. This and Dragon, I use it like every day and all the time. So if you guys haven't heard or tried, you please try out these tools. It's amazing. It also helps that the author for Dragon, Omar, is who also works at Meta, and both of them, Anji and Omar, they sit next to me. So it's been amazing to kind of ask them questions on how to use these tools. But I highly recommend trying out these. Cool. Any questions? I have more to share, but yeah, any questions on these on RedSnoop? Yeah. Anything that you can kind of kprobe onto, you can also use RedSnoop. It's built on the same infrastructure. It's just easier than doing it using BPF trace or whatnot. Yeah.
Yeah, I was thinking more like perf trace. The perf tool itself will do syscall tracing. It includes return trace points.
Yeah. So
what's the difference on that?
This works for more than just syscalls. It works for almost any function in the kernel, as long as it's not inlined. And for inline functions, I also have a hack where you can put in like some code that tells the compiler, don't inline this, which is one downside, I think, for this. It doesn't work well for inline.
Okay.
Mm-hmm. Yeah. Cool. And then I guess the second one I want to quickly share is ChatGPT. I mentioned this maybe at some point that... Yeah, so I was saying when I joined the kind of working on kernel, I was new, and then I actually use ChatGPT a lot, and you can kind of evidence by the number of questions I have asked it over the course of, I guess, the last year. And I just want to demonstrate a couple of ways that I use it. One way is to like explain, I guess, like command lines. Oops.
Polite.
So yeah, this is one I use fairly often, and you can just ask ChatGPT, please explain this to me, and it will explain, every flag. It will explain what the parameters do, and it's not always correct, but for someone who, it's close enough, and it often is like it gives you a starting point, so at least reduces the search space from infinity to, okay, now it's a more bounded search space for what the problem is.
I was just gonna say.
Okay, maybe we can turn this. Give it some questions. See how well it does. Yeah.
What is the classic TC failure? E-invalid. Why does TC get E-invalid?
Work. Hello. Oh, there. Here. It's off right now.
Okay. Well, there you go. There's a couple of answers. And I guess another tip and trick is if you want to, like by default, you only get the free version, you only get ChatGPT 3.5, and you have to pay $20 a month for ChatGPT 4. But one way around it is you can sign up for like an API account with OpenAI, and you can then kind of like you can pay per use, like pay per token. And you just load up with some credit onto your account, and you can use the playground and kind of issue API requests. And then that's like a cheaper way to use the use the GPT-4 models. The other advantage is that they promise that they won't use this playground information to train their models. So maybe it's safe to put sensitive information in here. I'm not sure, but I've definitely never done that. So okay, cool. That's all I had. Thanks.
All right. Well, thank you.
All right, so so the demo, I'm going to show, I've got automated virtual topologies and KMU launches of my development kernel, an interactive mode with that. I can do packet captures, debug with GDB. Everyone can do that, but I'll show you how it sets it up automatically. Basically, all these things happen very easily. Code coverage, profiling with flame graphs, and tracing. I'm going to give these slides out, and all of this stuff is available on GitHub, so you can download it, grab it, and use it if you want.
Hey, Christian, can you put your slides into the presentation mode, please?
Can you what?
Can you put the slides into presentation mode, please?
Oh, I see. Yes.
It'll help our old eyes. Thank you.
Yes. Is that better?
Much better.
Oh, great. Okay. So let me. So there's the code, and like I said, I'll put these. I'll send these wherever they need to go, so people can look at them. So the main tools are MuNet, which is a sort of testing. It's a simulation. I don't know how to describe it. It does a lot of stuff. It's sort of like MiniNet and some other tools that have been created. And it does things like launches topologies, wires them up, launches KMUs or containers or namespaces, runs code in them. And then PyTest uses that to drive it. And I use PyTest to drive that. So the tools that are used by the above are tmux, which is so it can open up windows during your session. It uses perf and flamegraph for profiling, tshark and wireshark for packet captures, GDB, and the native code coverage. Really quickly, MuNet has a config file which defines the topology, kinds of namespaces or KMUs. It launches and configures in nodes. I'll show that and connects them together again, it uses tmux and those other tools. So this is the topology I'm going to launch. It's a two host, 2 router topology. I've been working on something called IPTFS. So it's running an IPsec tunnel with this new IPTFS mode on net 1. So the topology definition is below. That's what you give to MuNet, and it creates that. And if you look, it says like kind, and it says, oops, oh boy, Linux and kind host. Well, the Linux here, this is going to launch. You see it launches the VM Linux. Oh, that's my GDB command. So the KMU args are booting my image and a root file system that I built. Command line arguments, memory, so forth. The GDB stuff comes in later. Okay, so that's it. These are like what I'm gonna do, so that people can go back and look later. Okay, so let's move to the demo. That was me. Okay.
Would you be able to increase your font, please?
Yes.
Thank you.
Yes. Okay. So let me get back to my outline on my other screen so I know what I'm doing. All right. So the first thing I'll show is an interactive mode. So again, you remember that topology? I'm going to launch that. I'm going to launch that with test simple. This little square is in my way. Let me move it. Test simple net. So this will launch and then pause. I'm going to go to one more, and then I say CLI. So now I'm at a CLI. I can do a lot of things, like I can open a console to router 1. So now in that, remember the router 1 and router 2 were in the center. So I can now look at, for example, my IP route, or since we're doing IPsec, let's look at the IPsec. This is just was configured by the test above when I ran it. So this is my IPTFS tunnel. Right there, you can see IPTFS ops. And then we can like ping 10.02.4. That's the host on the through the other router. Okay, cool, right? So yeah, that's about that. You can do a few other things in the CLI. Interestingly, like you might be able to. No, okay. I think we can actually pull up a packet capture. No, okay. So anyway, the interaction is mainly for the console stuff. You want to drive things. And the other thing you'll do is, for example, let's do a packet capture now. So let's add pcap equals net 0 and net 1. Now remember, let me pull up the picture. So net 0 is the host to R1, and net 1 is the IPsec link. So I'm going to capture on both of those. I'm going to run the SimpleNet test in pause mode, so it means I'm going to step through it. For some reason, my font might be too big or something. I don't know why it didn't just open both windows. So let me try it again without pause mode. I just ran this and it worked. Yeah. Okay. So it's running through the test right now, and you'll see it doing pings. Oh boy, I need to pause at end. Pause at end, so they don't disappear. You'll see the pings are on the below, and the IPsec link is to the right. So you see the ESP packets. Very cool, right? Did almost nothing to get all of that. So let's go ahead and finish the test, and then we could do like sudo. Let me change the ownership of the test of the capture files. Capture. And then I think I might have had this already in there. So let's look at the, I can't really make these, I don't know, can I make these bigger? Yeah, I don't know how to do that with X. Oh, there we go. All right, so you can see here, these are the ESP packets, and I actually have a Wireshark decoder for IPTFS. So it's actually decoding because I gave it the keys. It shows the encapsulated packets. Cool. All right. Next up, we want to debug something, right? So let's let me just copy and paste the line. So we want to debug a live action thing. We're going to run the simple net test again. We're going to say launch GDB against the kernel running R1 and set a breakpoint on IPTFS NQ. Let's see what happens. Okay, we got a tmux window with GDB running. It's gone and set that breakpoint, you can see. So this is it's an NQ when a packet comes in. So let me move up to the pause, and I'm going to go, and it says ping. Okay, a ping went through. Oops, it just broke. So there I am debugging my kernel with a packet. It just came through. Now, if I continue, you'll see that it passed the test because the packet went through. If I would have waited long enough, it would have timed out. So that's debugging, simple as pie. Code coverage or profiling, I'm not sure which people would rather see because I don't want to take too much time. I know I can take a lot. I'll do code coverage. That's pretty cool. So to do that, I need to rebuild my kernel. Oops. Yeah. And just to enable the coverage, in the kconfig options. So that'll take just a second. And what this is going to do is the only other change that you make, I'll show in the slide, is you add. Oops, why did we go past? You add this gcov under profile equals y to the make file of a subdirectory of something that you want to capture coverage for. So in my case, I want to do it for the transform code under networking. I should have built this kernel before. Sorry about that. But it's almost done. The other thing I'm going to show is flame graphs. And then I have something to show also tracing, but that's not that exciting. So I think I'll just do flame graphs and wrap up. Okay, so compile super fast and link slow. I guess that's because it's using 20 cores to compile, but just 1 to link. What I'm going to end up showing is I'm going to run the test with this coverage flag. It's going to go generate the coverage will get generated, and the tool actually just goes in, peeks into the KMU and transfers out the coverage data. And then I'm going to run an extraction script on that data, which just automates. There's these dumb steps you have to do, right, to extract the coverage. And then the last thing I'm going to do is show a coverage mode EL mode in Emacs where it shows the coverage actually highlighted in your source code. So let's do that. So enough. Run the test. Oops. Actually, I want to run it with verbose on, so you can actually see it. Pull the coverage out. So there, it's grabbing it, and after that, we just need to run the script to extract the coverage. And then I have this one last, you have to set a, for the Emacs thing, you need to point, why am I not typing Linux? Net xform. You just need to give it this coverage info link to the thing that just generated. So now let me go to Emacs I'll go into that directory. I'll go to my IPTFS code. Oops. IPTFS. Thank you. Oh, I already had the coverage mode on. Let me turn it off. Oh, yeah, there we go. It's on. Oh, it would already marked up the screen. So what you're seeing here is everything in green got run during that test, and everything in red was not covered. So typically what I do to actually use this is I have a whole suite of tests, right? And as I've developed this feature, I run my whole suite of tests, and then I come in and look at through my code and make sure that my coverage is good. And for things that I haven't covered that I want, I'll go write a new test to make sure I get that coverage. That's how I've developed this feature, and also gives me a lot of confidence that I've tested everything. Okay, so the last thing I want to show is the flame graphs. So that one, I'm not going to rebuild the kernel. I usually do the flame graphs with a fast config that has all the debug turned off, but we'll skip that. So the graph is going to be a little fake, right? Because it's going to be slowed down in a lot of weird places. So if I do flame clean, that just cleans up all these files. If I type make flame, it's going to run a test that I've told it to run inside the make file. Other than that, it does that profile flag. If you can see on the screen here, it's adding that profile flag, and it's running an iPerf client. So I usually do this actually with SRIOV and physical interfaces, and I'm able to on my machine. I don't know what that error is. Ignore it. I'm able to get like 7 gigabit performance in KMU VMs using SRIOV over IPsec tunnels. So it's pretty impressive. Okay, so this went and it used the flame graph tool. It got perf data, munged it around, created SVG. This is pretty set to my system. It's actually SCP'd it to my system. So I'll go to Chrome now, and let's open that file that it just transferred over. It's under chops, and then it'll be flame R1. And here we have flame graph. And let's see, for example, IP. We got IP output here, and let's see if we can find an IPTFS. It might be hard to find, like I said, because so much stuff is. Well, in any case, if I ran this without debug, it would have had some. You would have been able to see some IPTFS functions. But this is pretty cool. I think everybody's familiar with flame graphs. They're very useful. For example, when you look at this, this empty spot above here, that means this function's running in that and not doing anything, not calling anybody else. So it's a good thing to look at to optimize, and so forth. Okay, like I said, the only other thing I had was I have a way to run the test, and it does tracing. So instead of the old printf mechanisms, we use traces now, and it'll go extract the tracing. It'll enable it and extract it from the running thing and put it in a log file. Okay, that's it. That's my foo.
Any questions? That was some pretty cool stuff. Jamal.
Yeah, Christian. Do I have to use Emacs?
No, well, that's only for the coverage markup thing, right? Other than that, like if you notice, like GDB just opened a tmux window, right? And you could run it in TUI mode, to get like source views. I will say that if you do use Emacs, there's also a really fancy feature called GDB in Emacs, and it will actually launch the many windows interface. So instead of being in the tmux window, it'll be, in Emacs with the 5 windows and local variables. It's pretty cool because that's a lot of setup normally for a kernel.
Just one question: can you also use it, with the pass-through devices to debug the driver as well? And do you have any samples that would show how to set it up?
I have not used this with. You mean with physical devices?
Yeah.
Yeah, I have not used it with physical devices. No, it's been primarily designed for KMU right now. Yeah, that would basically be an extension to MuNet. And there is some code there to do SSH and stuff, but yeah, it's not. I'll just say it's not set up to do that right now.
Okay.
Christian, this is Dave Tott. I really wish I'd had this tool 8 years ago. And I love that you use Emacs. But I have a question for you. What version of iPerf are you running?
I'm running. I run both iPerf 2 and 3. I don't know that. Do you mean like 2 or 3, or I don't know what version?
iPerf 2 is what you're probably running, and over the last 3 years, we put a lot of really cool tools in it for measuring latency. There's a new bounce back test and a few other tests, which would be very interesting to pour through your IPsec tunnel.
Yeah, thank you. I actually, in my, if I showed you my test, you'd see I actually have like an if statement. So I can run iPerf 2 or 3.
Cool.
But I'll check those features out.
Go Googling for the latest version of iPerf. Came out a few months ago. Thanks.
Awesome.
Any other questions? All right, well, thank you.
Thanks.
Okay.
Hello. So I'd just like to say thanks for Chris, because he actually wrote a bunch of the stuff for our project, and we use his tools all the time. They're great. You should use them yourself. The one thing I would like to talk about is have anyone heard of the RR debugger? No? Well, there's one. Okay, that's good. So what it allows you to do is to record your program and then play it back and stop it anywhere you want. And if you want to, and you could also go backwards and look at everything in the program that happened. So it's a really cool debugger, and I would suggest you go look at it. That's my...
All right, cool. Well, thank you.
Okay. I am going to show something very trivial.
Introduce yourself.
Hi, I'm David. I work on FRR. Hi, David. So the Linux kernel has this extended printf thing. I'm pretty sure everyone here knows it. We thought that is a good thing. We copied it into FRR. Now, the problem with this is you don't get any type checking from GCC. So if you change something here and you build it, the code is correct right now, so you're not going to get any warning, as seen here. Now, if I do this wrong intentionally and compile this, you do actually get a warning, which, if you think about this, how does the compiler even know? And the answer to that is, we actually ended up writing a GCC plugin that does type checking for exactly this thing. It's in the FRR source code. It works together with this. So the plugin reads these pragma, whatever, and the pragma tells the plugin that PI4 should be in adder or in adder T. PI6 should be in adder 6. And then the plugin, if you get it wrong, you get the warning. It's pretty easy to build. Let me just clean this up. How many kernel errors did it find? I haven't tried using it against the kernel. So it's a single file. It's actually a copy of GCC's standard format checking code. I can show it. It is incredibly ugly. So, first of all, it's GNU code style. Yeah, I don't know, like there's tables like this. Because it's a copy of the original format checking thing, it includes everything and then just adds on top the pointer checks. And I think that's it. You can find this on GitHub. Let me click over here. FR routing, FRR, tools/GCC plugins. It should work for the kernel. I don't see why it wouldn't. You're probably going to get a whole bunch of warnings if you try to enable it. You do need to go and put together the pragma things for the specifiers because they are different between FRR and the Linux kernel. And that's it, really. Questions?
You didn't add in the C.
The C? Oh, I don't think FRR supports that. Oh, actually, no. That's not here because it's the same type. So flags don't need to be in this. Yeah, so. Other questions?
Thank you very much for sharing.
Okay, I would like to tell you about something that actually, of all the things I've done in my career, this may be the one I'm most proud of. It's incredibly small and simple, and yet incredibly valuable. It's the fundamental thing I use for all of my performance tuning and much of my debugging. And it's called time tracing. So the idea is really simple. You decorate your code with various calls to a routine called TT record. So we have one here. And what this takes, it looks kind of like a printf statement. It takes a format string and then up to 4 additional arguments. What happens when you invoke this is the time trace package, it does not actually call printf or format the string. It saves that string. It's a static string pointer, so it's not doing a string copy, just saving a pointer, plus the values of those 4 arguments, plus the high resolution timestamp counter, plus your current core identifier. And it saves these in a big circular buffer. And so you just put these TT record calls all over your code at interesting points in time. And it's free running, filling the buffer, wrapping around on the buffer. And then you can read the buffer out and dump it. And when you dump it, then what it does is then it calls printf at that point. And it combines the format string with the arguments and produces this output. So the actual TT record calls are extremely efficient, about 10 nanoseconds. So I use this for nanosecond, when I'm doing nanosecond granularity debugging for things like HOMA, I can get this very accurate stuff. Then if you look at the raw output file, so here's an example of one of these. And what you see is you see on the left side, this is the timestamp. They get converted back from the TSC things in microseconds, the gap from the previous record, the core number on which this executed, and then that formatted message. Okay, now if you look at this, there's a ton of data there, but then what do I do with all of this? It's just a huge blob of data. The next step is I write Python scripts that will parse these trace files and combine them and manipulate them all sorts of ways that are really, really powerful, just incredible. And I have some standard ones that I use over and over again, and I'll often write custom ones when I'm chasing a particular bug or timing glitch. So for example, one of the most useful general purpose ones is called ttgrep.py. So you may notice in these timestamps, when I'm tracing HOMA RPCs, they have identifiers. And so the text ID, yada, 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 will appear pretty frequently in the trace files. So I can invoke ttgrep.py, and I say, basically extract out all of the records that have that information in them from this particular trace file, and then it also reformats that to recompute all the time differences. And so if I do that, then what I get is basically a trace of exactly what happened for this one RPC, its entire lifetime going through the signal. Again, at basically nanosecond granularity, I can look and see, oh, here's a pretty big gap here before, I had to wait to send the grant out. That's probably unfortunate that was delayed, and I skim down and see, oh, wow, look, here's another big time. Took 50 microseconds to copy data to user space. So you can see whole bunches of information now, and you can look at the lifetime of something in incredibly fine detail. The next step is there's a call called ttfreeze, which is really valuable. If you invoke ttfreeze, it does what the name suggests. It freezes that time trace, so no more records will get added to it. That's really valuable because you can put ttfreeze in when interesting events happen. Like, for example, an RPC takes an unusually long amount of time to complete. So I have code in HOMA which have a little threshold. If an RPC takes longer than that, it'll freeze the time trace. Then you can go back and extract it out, and you can see exactly what happened over the life of that RPC to see why it took so long to happen. The next step is combining time traces. So when HOMA is running on a cluster of servers, they're all filling up their time traces. Well, I have a cluster freeze command where you start it on one node, it will freeze locally and then send messages to all of the other nodes in the cluster, and they will all freeze their time traces as well. And then I can extract out all of those time traces and start doing analyses on them. Okay, so the next step is, well, in order to analyze these, if I want to combine the time traces together, they're all running on separate clocks, one for every machine. Well, I've written a script called ttsync.py. Let me start that running here. and you give it a list of time traces. This will take a second to run. It reads in all the time traces, and then it synchronizes the clocks and rewrites all of the time traces but the first one with clocks that are synchronized to the first one. And the way it does that is it can look at packets, since it sees packet identifier, it can see a packet getting sent on one machine and received on another, and it can analyze the time differences of those with packets going in every direction in order to compute, as you can see here, to compute the minimum. Well, for each pair of nodes, it computes the minimum time to get from the first to the second, the minimum time to get back. Sometimes those times will be negative because their clocks are misaligned. And then it can compute the round trip time and figure out an offset to basically make those clocks line up. So now we have a collection of time traces from a whole bunch of different nodes where the times are all on the same time scale. So I can follow RPCs across the system and see what's happening on different machines. So then the next script I want to run is this is a script a general purpose script with a whole bunch of HOMA analyses. No, not that one. Let's see. So this script is going to run what's called timeline analysis on two time traces I've gathered previously, a client and a server. The client is sending 500K RPCs to the server. They're all the same size. What this will do is read in those time traces and then compute a timeline for each RPC of interesting events. So it collects all the RPCs together, and it will tell you, for example, how long does it take after the client invokes send message before the first packet goes out. And it'll say, well, this is the average time, and it also shows you the P90 time if you want to look for extremes. Well, how long did it take before we got our first grant back from the server? Well, on average, 25 microseconds. The P90 time is 33.7 microseconds, and so on. So now we can see the lifetime of an RPC, both on the client and also it shows the same things happening on the server, exactly what's going on. So we can see, again, in very fine detail exactly what's happening for these RPCs. And there's many more analyses you can do. I'll show you one more. This one will take a few seconds to run. This is going to do an analysis of the network traffic between, this is on a 10-node cluster, where I was seeing delays that didn't make sense to me. I was trying to figure out why are these long delays happening. So this is going to read in all of the time traces. These time traces have already been synchronized, so the clocks are lined up. And it's going to analyze all of the flow of data packets from across every pair of machines in there and print out some overall statistics on that once it's finished reading in the 10 traces. A couple more to go. Okay, let me scroll back up to the top and explain what this information is here. Oops. So first of all, it prints out information for every one of the nodes and for every core on a node that received packets. So this is every core that received packets at NAPI level. It will compute, first of all, how many packets did that core receive? What was the average end-to-end delay from the sender to us actually getting the packet on this node? What was the worst case delay? And it will also print out, here's the time in the time trace file for that worst case delay. So if you want to know what that is, you can now go back to the time trace file for that node, look up that time, see what RPC that was, then use this ttgrep to extract all the data for that RPC and see exactly what went on in that RPC, where was this huge delay occurring. It also computes the average backlog. That is, how many kilobytes of data are in transit from any sender to this particular receiving core on this particular receiving node at any given point, and what's the worst case? What's the worst case backlog? And again, when did that backlog occur? So I can go back and look at the trace file and extract out more details for all of that. And you can see this data, it has this data for every core and for every node in the whole trace. So these are just examples to give you the flavor, but it's just an incredibly powerful tool. I use it not just for performance analysis, but also for debugging. If I'm trying to figure out what happened, how did we get to a state? You can't set breakpoints to figure this out because everything's happening too fast. So instead, I just lard up the code with time traces, detect when the problem has occurred, dump out the time trace, then I can look back in time and see exactly what happened and why that problem occurred. So it's really simple. It's like 200 lines of code to implement all the core time trace stuff that you see here. And I've been using this in all of my projects now for about 10 years. And it's my #1 debugging and performance analysis tool. Yeah.
Oh, I got it, BJ.
And by the way, I should say I have this not only in Homa, but I have a whole bunch of time traces I've added to my Linux kernel as well. So I can register what's going on in Homa with what's happening elsewhere in the kernel also.
So do you have the clock synchronized between all those machines through the White Rabbit protocol or something like that?
No, don't need clock synchronization. I can synchronize using the time trace records. It turns out there's enough information in the time trace records to synchronize the clocks because I can see packets leaving one machine and arriving at another machine. I can see packets leaving that machine and arriving at the first machine. And using that, you can basically compute the offset between their clocks. And it works, it's amazingly accurate.
Were you able to figure out differences amongst this tracing mechanism and like the trace buffers in the kernel? So there's like trace print K and et cetera that already does all this ring buffer stuff and all the nanosecond printing, et cetera, et cetera. It's all built in.
Partly out of ignorance, I have not, and partly because I've had time trace for a long time, and so I'd already been using it, so I just pulled it over. So if trace K does the same thing at the same performance time granularity, then oops.
No, I was just wondering because it looks like it was pretty similar and a built-in thing in the kernel. So you would be able to build all your existing scripts on top of that thing. It just does ring buffers for you.
No, but would trace point replace? He's almost doing like print Ks in the code. No? It is similar.
Yeah, it's what that's what I was going to say. What Jesse said is exactly it. So it's not an oops. It's just that there's a maintained backend which you can use, but all the stuff that you've done, which is the analysis tools, is new, and we would love to see that. I think, to your point, right? Even the fact that you're doing phase-based time adjustment and locking against nodes is huge. I mean, we could use it every day.
There's a remote.
I mean, so does this assume kind of a static RTT between these hosts? That's like, or there has to be some fixed time thing here, right? Like you can't just end up, calculating the synchronization between clocks unless you know the exact propagation or your propagation accuracies. It limits your time drift accuracy, right?
No, don't really have to know any of that in order to synchronize the clocks because you just measure the transit times as observed separately these individual clocks. And if you look at the transit and pick the minimum, basically across the whole trace, it finds the fastest one and uses that to synchronize the clock. That's the key thing.
Yeah, for sure. That's what I was looking for. That's what I've done in the past.
Then you could pick a slow one, and that could mess up the synchronization. You have to find the fast one. And actually, when synchronizing, it's a little bit trickier too, because when they're synchronizing a bunch of nodes, it may be that if you pick just two nodes, A and B, the performance was so bad that in fact you can't synchronize those nodes. The minimum time is still high enough to create high error.
Right.
But when I've got a collection of nodes, all I need is some node I can synchronize with. And so everybody has some other node that they have relatively fast communication with. And so you kind of pick pairs of nodes, pick the way you synchronize, starting from one base, until you eventually reach everybody through some path of synchronization with other nodes.
And when you have deviation from the minimum, are you saying that you're attributing that all to network delay and none, or performance delay and none to clock drift, basically?
Yes, that's right.
Okay.
If there's deviations from the minimum, it must be some factor other than clock offset. It's got to be some delay someplace in the system.
Cool.
Okay,
now we are debugging our running kernel.
Unfortunately, we can't see your screen. It's disappeared again. Is it showing there?
It is showing now.
I think.
Okay, now we're good.
I get it back, I think.
Yeah.
So basically, this prog is our running Linux kernel, and so we can look up whatever global variables we want. For example, how many CPU cores do I have in this system? It's a 64 cores, and it's a unsigned integer. Like other things, for example, what is our host network namespace, uniquenet, as we know, it is a huge structure, but you can see basically everything printed out in this Python interactive session. And do other things like, for example, what about our E0 net device? We have a helper function called netdev get by name. Oh, sorry about that. Yeah, so this worked. This is our network device structure. And we can print out interesting information from it, like what's this root QDisk. Looks like we've installed a MQ or multi-Q QDisk as the root QDisk of ETH0. So yeah, basically that's it. It reads kernel memory from the K-core interface and parses it using like dwarf debugging information. So now I'd like to show you how I use the Dragon to troubleshoot a kernel issue, kernel networking issue using a unrealistic or oversimplified setup. So in this setup, we have two network namespaces. One is host, one is pod, connected using a virtual Ethernet or VEF pair. And on the host side of this VEF pair, we install a TBF QDisk, which is a traffic shaper that rate limits all traffic to 100 megabits per sec. So this is pretty basic, I would say, a traditional way of rate limiting things. Now we have other ways of doing it, for example, HTTP or eBPF-based solutions called EDT. But yeah, this is just for the demonstration purpose. So let me set up this real quick. Yeah, it should work. I just copy-pasted everything. I cannot remember IPR2 commands anyways. So we start the server inside the pod, and we start a client outside the pod, and using UDP and using this -b option to say that, hey, I want to send at 1 gigabits per sec. However, it is only sending 97 megabits per sec as we enforced the rate limiting. Yeah, everything works just fine. So if we are going to do something more interesting, we may use a different design. Instead of installing a TBF QDisk on the host VEF, we instead use a TC mirror action called mirror or redirect action to redirect all destination port 8888 UDP traffic to a IFB device in the same network namespace and use TBF traffic shaper 0. So in this way, we can choose which kind of traffic we'd like to rate limit. So everything sounds good. So let me just set this up. So first we need to delete the TBF QDisk on host VEF, create a IFB and set up redirection. Finally, attach the same TBF QDisk to the IFB device, like shown in this diagram. So now the server is still running. What if I run the same iPerf client again? The server side kind of works because it's still receiving 97 megabits per sec. However, the client is sending 1 gigabits per sec, and 91% of the traffic just dropped. So this is the issue. I was wondering why this would happen. So the way we troubleshooted this issue is by using Dragon. So let me run this client for a little bit longer. PID of the client is blah. So in Dragon, I'll just assign that to a variable. And let me copy paste all of this. So for example, we have this find task helper, which given a PID can return the task structure in the kernel. For example, PID 1, now I have task, and task.com is systemd because I'm using systemd, right? So back to our example. So it is traversing all files opened by this iPerf client. And for each opened file, we check the corresponding inode if it's a socket or not. If it is a sock, we go ahead and use this containerof helper function, just like we're used to in the kernel C code. And we get the containing socket alloc structure. Then we access its socket and its sock. So now we should have a, it just happens that I know the first opened socket will be the sending UDP socket we are interested in. But with all those informations, we can do extra checks, like checking the corresponding INET sock, the protocol of it, the destination port of it, but I will just skip all of those for brevity. So now we have this socket in question. It is sending a lot of packets. So here comes the hard part where we actually spend a lot of time staring at screen and talking to my colleagues. So finally, we figured out that something in this socket is strange. It is the SK writemem alloc member. 1. So what does this member mean? It means all pending packets that belongs to a socket. Let me go back to this diagram. For example, a UDP socket transmitted a packet, then this SK writemem alloc value should be increased. Then it goes through all the way along the network stack or being queued in QDisk. And finally, when it left this, and when it leaves the system, the SK writemem alloc is decreased. In other words, this member actually shows how many packets are there pending in the system. It left the transport layer, but haven't been sent out to the internet. So this value here is 1, which is abnormal. So basically, the UDP layer code is looking at this value and thinks, okay, so it sounds like the kernel write queue or the pending queue is empty, so I can keep sending as fast as I want. So let's stop this client and move back into our previous setup. So this should do the trick. Making the IFB device and now if we run the client again, it should work as expected. The server receives 97 and the client only sends 97. Now if we do this lookup again, PID of the client, oh. Yeah, now as we can see, the SK writemem alloc of this normal UDP sock is actually a pretty big value. So that is different from our previous setup. So in this case, the UDP implements a kind of sock back pressuring mechanism by looking at this number and okay, I've already sent a lot of packets that are already pending in the system, so maybe I'll just slow down. So with Dragon, we can easily print out the value of this member in both scenarios. Yeah, so basically that's it. And more about why this second mirrored redirection doesn't work is because it actually clones the SKB, and it redirects a cloned SKB to the IFB device, and these increase and the decrease ping pong does not include a traffic shaper. So the traffic shaper, the cloned SK buffs are not accounted for in the SK retmem alloc bookkeeping of the original SOC. So basically, UDP, whenever UDP send faster, the package just gets dropped faster. So yeah, some might argue that there might be other ways to troubleshoot this issue, but in my opinion, I think Dragon is the easiest way, and I just love it, and I hope this has been interesting to you. Any questions?
I have one. Can you scroll back up to you setting up the TBF thing for me, please?
You mean this one?
No, you setting it up, the actual command line you gave.
The actual.
So scroll up on your. So you, no, the actual setup of the HTTP. So the TBF thing that you did. So repeat that command for me if you could, please. But don't hit enter yet. This is my foo. So, what are you trying to do? Okay. All I wanted you to do was do tc qdisk add dev whatever root cake bandwidth 100 megabit and repeat the test. Cake has been in the kernel for about 8 years now and has all kinds of really useful statistics in it as well. Similarly, you are adding 50 milliseconds to a path inside the kernel by using TBF in this way. So if you were to take a packet capture of how this stream was performing, it would be doing this enormous sawtooth that it doesn't need to be doing. So I'm serious, could you actually put in cake in there and tell me if it works? So TCQ disk add dev host feth handle one root cake.
Yeah, I don't know how much time we have.
Oh, come on, just one line.
We want our pizza and then our cake.
A buffer blot cake. Should have seen it.
There, while we're
bandwidth 100 megabits.
Uh-oh. What is he getting beta numbers? Dave, I'm sorry, a lot of packet reordering here. Is this cake doing it?
Okay, Tom, you have a question? No? Okay. Other questions? All right. Well, hey, I want to say thank you to everyone who was brave enough to attempt to slay the AV beast. but also come up and share some tips and tricks with folks. I think there's some really cool stuff. Maybe we can do this again next year. All right, thanks.